o'clock on Friday, so it's time for Coffee with Karl. I'm Karl Dye from Tridec. We've got a special guest this morning. Dr. Vince Sprenkle is the Senior Advisor of Energy Storage from PNNL. Dr. Sprenkle, welcome.
Thank you for having me. It's great.
You bet. And before we went on, you said that I could call you Vince, so I'm going to take you up on that.
Please do. Thank you.
I've been looking forward to this conversation for a long time. I think, we all read a lot about energy storage and renewable energy and how can storage, make a difference with that. So really looking forward to this conversation this morning. I'll remind our audience, if you do have a question and you're on Zoom, you can use the question and answer feature at the bottom. If you're on social media, you can ask questions in the comment section, and we'll do our best to get through all the questions that we have this morning. So it's a tradition on Coffee with Karl that we talk about coffee or our mugs this morning. And my wife found this mug for me this morning. It is Peanuts Christmas, which I think goes along with the cool music that Tracy just played for us. It's a pretty cool old school mug about peanuts. I've always loved peanuts since I was a little kid. Our kids love peanuts, and I think it's a good way to get ready for the Christmas next week. So Vince, do you have a coffee story, mug, or anything else you want to share with us this morning?
No, I got my my favorite mug so far, the one that my kids tried to steal. I picked this up at MIT, and if you look closely, it's
awesome.
all filled with periodic chart and kind of all the things in engineering formulas and stuff like that.
That's cool.
We were walking by the campus store there and went, I got to have that. That's coming back with me.
Oh, that's really cool. Well, let's kick it off and just tell me a little bit about yourself. Like, how did you come to PNNL in the Tri-Cities, and what's your backstory?
Okay, so next month will be our 20th year in the Tri-Cities.
Right.
January of 2001 we came out here. So my background is, by training, I am a ceramic engineer. Went to the University of Missouri Rolla, which is now Missouri Science and Technology. And did that, and then went out and worked in industry for a few years in Iowa, and then had some colleagues from grad school that were working out here at PNNL, and they kind of recruited me out to work on a fuel cell project that we had going. And so awesome. I spent about the first 10 years of my life out here working on fuel cells, that type of work. And then slowly got in there you have the electrochemistry background that's very similar to batteries. Yeah. And then as we started growing the battery program here, was able to shift over in development. And then really over the last few years, it's been much more in terms of, coordinating the research efforts, working with headquarters, as they try to define a larger footprint for energy storage. And so that's been my real role in the last few years.
Well, that's awesome. I think a long time ago back in Chicago, I worked for Caterpillar, and I think a couple of people I worked with were graduates of your same college at Rolla, yeah. University of Missouri. That's awesome. It's interesting the how you pronounce Rolla, right? Because it's not spelled like that, but every place we come from in the country, so we have our own pronunciation of a word that's spelled and pronounced.
Yeah.
And then, so you said you worked in private industry in ceramics. So what kind of company, or what, when we think of ceramics, obviously we think of like coffee cups and stuff, but ceramics obviously have an industrial application. Was that kind of what the field that you worked in?
Yeah. So what got me in it, there are, most ceramics, glass and other things are electrical insulators in there, and they prevent charge from flowing. And so you see these on your voltage lines and everything, but you can manipulate the atomic properties of a ceramic to actually conduct electricity.
Oh.
And typically you can do that at much higher temperatures. So as you're looking at something that needs to conduct electricity at 1,000 degrees C and be stable, you can actually, ceramic works better in those environments than you would have in a metal.
Wow.
And so my research focus was on manipulating those to either conduct electricity, or the other thing you can do is you can start putting defects in it so it can conduct oxygen through there. And so the company I was working with, we were trying to take these ceramic materials and basically take air, which is 21% oxygen, and concentrate it for medical high purity oxygen to generate 100%. And so you've got no moving parts. You've just got a ceramic membrane basically that is separating and concentrating the oxygen out of air. To do it. And so this was for, you can see applications if you were in a chemical biological area, you could get a purified oxygen stream out of there, out of a contaminated air source.
Okay. Wow, that's we could probably spend an hour talking about that. I don't want to get too deep on that because it's really intriguing, but I will ask you another question before we kind of get into more of the grid storage and the electrical system. But we've had in economic development that we do at TriDeck, we get requests for inquiry, and sometimes, in the past they're very general. A lot of times they'll come through Department of Commerce, or we'll have a direct contact with the company, but interest, in potentially moving into the Tri-Cities for like battery companies. And I know one proposal that we looked at was a company that would go into like using silicon, which I think relates to ceramic, in battery electrodes, cathode, anode, and stuff like that. And I don't know anything about it, but I'm just going to ask you this transfer from, I think a lot of electrodes today are maybe graphite in like a lithium ion battery or something, and then moving into silicon. Can you just briefly hit on that, on the advantages of maybe going to those type of electrodes, and then, what some efficiency gains or capacity or difference in that, like why that would be a big step?
Yeah. So when you look at, especially lithium ion batteries, kind of the state of the art today, what you're buying, if you buy a Tesla Powerwall or one of their cars, is a mixed metal oxide cathode. So that's going to be like nickel, cobalt, aluminum, or what they refer to as NCA. And as you pointed out, that's teamed with a graphite anode. For reference point, that's about 250 watt hours per kilogram of weight of battery. And so where that energy density or specific energy density comes into play is how much energy I can pack into that weight of batteries, that if I can improve that, I can improve the driving range of electric vehicle.
Sure.
Or I can improve everything for that same unit of weight. And so what silicon gives you in that is, by replacing silicon, the graphite with silicon, it can hold more lithium. And so it's a little bit heavier, but I can also get a ton more lithium in there. And so per weight of material, I'm able to store that much more lithium, and I get a higher energy density. And so you can start seeing that you can start taking that 250 to get it up to 300, 325, in those ranges with silicon. And so on an EV, I extend my driving time. In there. One of the programs that we've got at the lab is called BAT 500, and that's goal is to take that 250 that we have watt hours per kilogram today and take it to 500 watt hours. So you would essentially, for the same weight of batteries, be able to double the driving range of electric vehicle in there. That's not going to be done with graphite or silicon anode. And what we're going to do there is just go to straight lithium metal.
Oh, really?
On that anode side.
For the anode. Oh,
side of that. So that is, one of those really stretch goals to get, but it could have big impacts in there.
I mean, that's how science works, right? Like we always use the man on the moon analogy and President Kennedy and something, but I think in science or in our jobs, we don't get anywhere unless we strive for, reach for the moon, literally, right?
Yeah. We like to call those stretch goals in DOE. So
you bet. Well, that's great. I think then too there's a crossover into battery and electrical vehicle usage in different types of transportation modes then too, right? Like I know air travel has this power density issue with existing battery technology to be able to basically, and I think, and I'm not a scientist, so I sure appreciate your guidance. And if I ask any silly questions, you'll tell me, but the power density of liquid fuel, if it's jet fuel or gasoline or something, like you're talking about versus a battery, is a lot higher. And so that's why planes work, right? Because the weight of the fuel, they can still fly and carry a lot of passengers and cargo. And we need to get more power out of batteries to be able to do electrical airplanes, for instance.
No, you're correct. So just to go back to that point of, us trying to target 500 watt hours per kg, we would need to double, triple that to really start making some inroads into electric aviation applications. So there are efforts to use the current battery technologies now for electric aviation. Uber's and their unmanned drone system that that would fly you around, but those are relatively short. So you're talking 15-minute type operations. As you start looking at trying to get into, say, a regional 200-mile jet, then you've got to start looking 1,000, 2,000 watt hours per kilogram to be able to go to something that would have a 45-minute hour to hour range that you would have. And so in a lot of these, it's going to be difficult for us ever to have 747 purely electric powered. You're going to have a hybrid system. But what you can do, and we're seeing this not just in aircraft but in all industries, is hybridization. So can I put a battery system in that would facilitate takeoff and landing in there, because that's your biggest fuel usage. So if you're looking at decarbonizing the transportation fleet on there, you can have tremendous fuel savings by just augmenting the takeoff and landing with a battery system. We see it on the grid whenever we got to bring a natural gas peaker plant on to handle that flexibility. You can augment a lot of that with a battery storage system that would handle those 15-minute type fluctuations. And then you've still got the, I would say, the longer term energy assets that can come into play later. There.
So that's great. I didn't mean to go so deep into it, but I just couldn't help myself because and I think it does, kind of obviously connect to your education, and, your industry experience, which is great. Let's get into really, your present role, like you said, at PNNL with the different areas of grid storage and some of those great initiatives that are going on at the lab. Can you just kind of give us a general overview and really what's your scope today, and maybe hit on some of those key points like grid storage launchpad and what some of the goals are?
Okay. Yeah, I'd love to. So, so in my current role, I manage our grid energy storage portfolio at the lab, and that involves me primarily working with the Department of Energy headquarters, different offices. So primarily the Office of Electricity, which is steward for a lot of the grid energy storage work that goes on within DOE, but also cross-cutting that, with the water power, which handles our pumped hydro capacity and R&D efforts there. There is a strong interconnection with the vehicles program as what they're doing. And so, my goal right now is to, that we have R&D that is meeting what the mission needs are of headquarters as they've defined it, what is the best kind of agenda for the nation in terms of delivering on that kind of future challenges. A lot of what we do at the lab is trying to take that future view. We need to be working on problems that are 10 years, 20 years out, and developing those. And so that's really are we positioning ourselves that, we have the insight, we have the problem analysis and everything to really go and set up a 10-year plan to do that. So overall in grid energy storage, it's been over the last decade, really an increasing importance that we've seen throughout DOE in this. And then a few years ago, DOE started looking at it. We've started to see since 2008, a big increase in lithium ion batteries that have been put on the grid. That's the most recognizable technology that's out there, probably the most mature for grid applications. DOE started looking at that and going, at the end of the day, the U.S. manufactures very little lithium ion batteries. We do not have control of the supply chain. Lithium is sourced other places. And if you look at the projections, the US is going to be one of the largest consumers of grid scale energy storage as we get into that 2030 to 2040 timeframe. So how are we going to change that dynamic so that the US is a leader in this, both in the manufacturing and the deployment of it? And so DOE set up what's called the Energy Storage Grand Challenge in there. And that's basically by 2030 to ensure that we are the leader in the innovation, development, manufacture, and deployment of energy storage technologies. Mm. And so a large part of that is batteries, but then, that's also chemical storage. If you could look at hydrogen, the whole gamut. There's not one storage solution that's going to fit all of that. And so, that's been great. That's getting kicked off. Actually, we're waiting for an announcement from DOE that kind of officially kicks it off. It looks like that may be Monday when that all comes out. Awesome. But they've made, there is information on the Energy Storage Grand Challenge out there today and what their overall goals are from that. As part of that, and you start looking back, and so electric vehicles have been a topic of conversation for quite a while. Right. DOE has built up quite a bit of infrastructure to support that vehicle electrification across. So if you go to Argonne National Lab in Chicago, they've got facilities there to build out lithium-ion cells. There's EV testing facilities in Idaho. But there was a complete kind of materials to deployment aspect for electric vehicles. And so when they started looking at grid scale storage, there were some huge gaps in that infrastructure that we had in the R&D facility. And so the Office of Electricity basically set out to go, okay, we can solve that and what came out of that is the Grid Storage Launchpad that we are proud to be hosting here at PNNL. Yeah. Coming through, hopefully in 2023, we will be up and going in construction. And what that is to fill that infrastructure void that is in there on Grid Storage Launchpad. It is to be able to come in and take all these great ideas that are coming up, and can we validate them that they're going to work? Yeah. And that's a creative thing. My associate lab director, Judd Verdon, likes to tell the story of, every day there is someone solves the grid energy storage challenge, but in a paper or news release or something like that. But we still have a grid storage energy issue that we're not solving. So, we've got to have some way that we can, what are the best solutions? Yeah. What has a reasonable chance of doing it? And so that's really what the Grid Storage Launchpad is doing is, can I validate that? Can I validate it as soon as you develop a material? Let's give you an idea whether it's going to work or not. If you come to us with a prototype, we will put it through a rigorous use case testing and give you, yes, hey, this looks promising, or you have these issues. And so that's really what we're trying to do. The other thing is to provide those capabilities. So anyone in the country can come in and have access to the material synthesis, that they need. If they need a new silicon material for the anode, you mentioned earlier, or they need to develop it and put it into what it would be a industrially relevant type prototype, in there, we have those acts, but just having those core facilities available to the country to be able to use to develop this technology. Yeah. And to the point where we will test up to about 100 kilowatt scale systems in this new facility. Okay. And then you would look at 100 kilowatts is about the smallest size a utility will start to, I would say, look at as a real system. In there, it's kind of the minimum level to be grid interconnected in California, as they've defined it. So those are some selling points. Now, people may want to see, a megawatt scale system like's been deployed out at Horn Rapids, and then you have areas, other parts of the country, or even potentially at Horn Rapids, where you could deploy that type of system and get some validation measurements on that.
So you mentioned the Horn Rapids system just now. Could you give us just an overview of what that is? And you pointed out something when we were chatting before we started about the workforce development, and training. opportunity with the Horn Rapids site and kind of the team effort that pulled that off. And then I think you talked about another program that's coming out of DOE where they actually talk about workforce training and stuff. Can you kind of give us a, like, what's going to go on at Horn Rapids, and what is the significance of that with the 1 megawatt storage system?
Yeah. So and I need to make sure I got my numbers right, but I think it's a 1 megawatt, 2 megawatt hour storage system that's been installed out of Horn Rapids, and there's maybe some links we can provide on that.
Yeah.
Tied with us, the solar array out there. What's unique about it, though, is this is the first one that has a focus on the training aspect, and bringing people up to speed on how do you interconnect storage and solar, do that safely, do that appropriately. And so I really see that's a great opportunity that has been missing, in the country, in terms of just being able to get people trained in that.
Yeah.
From our standpoint at PNNL, it's been great to kind of have that, I would say, downstream development from what we typically do. We don't typically deal with large scale systems and do that, but we see the need for training. We see the need for information that can help inform what our R&D needs to do. So we have people that are involved with energy storage safety at the laboratory. And so, as they're actually learning things, and working with people to how do you train and connect these systems, we can learn things there too about how do we need to do research to help improve the codes that go into how you do that. Yeah. And so, but also, just having that connection between a strong R&D environment and a system that's deployed in the ground, and that communication that we've had, and we've had a great communication with Energy Northwest on this, and in terms of, we were working with them early to help with the economic assessments, what are the benefits we could get out of this and do that. But, just to have that communication and kind of that holistic, to go from a material to seeing how it actually interacts with solar and is tied to the grid, those are rare when you get kind of that holistic view of it. And, we're fortunate in the Tri-Cities to have that here, where you've got kind of a complete life cycle of a technology that you can test out. And so I think that's really a great thing for the region, that you have that kind of that entire life cycle represented here.
That's a great point. TriDec has partnered with many of our local entities and many of our TriDec members for years to host this initiative called the Mid-Columbia Energy Initiative. And we actually had a meeting this week, and that was actually brought up, that we are this unique point of view, that we have everything from the cutting edge research that you guys are doing at the lab into the generation, that for carbon free between hydro, nuclear, solar, wind, we actually have a good amount of generation here locally or within the region. And then, all the way out to the utilities from, City of Richland, Benton PUD, Franklin PUD. We've kind of got that whole gamut, and we do have initiatives, like the Mid-Columbia Energy Initiative I was talking about, that we all get everybody around the table and say, hey, what can we do together to do this, and look at it in what you guys are doing on the how do we build the technologies? How can we connect with companies that you guys are going to be working with in the future that come to test their technology, or to kind of get that verification and all the other things that you guys are going to do on the grid storage launchpad? Can we have a dialogue with those companies and say, hey, we're in the Tri-Cities, man, this is the best place to be for your company. Let's help you create some more jobs here. Like, it's just this cool, unique challenge. I don't want to, get too big on promoting ourselves, but I think we really have a great opportunity here for this, for all these things to come together, just as you described.
Yeah. No, I think you're right on. I think overall, we don't see storage is, I think, here to stay. Yeah. And we're seeing, as we were discussing earlier, we're seeing whether it's, from increased variability as there's more renewables penetration, or we need, we're seeing increased demand through electric vehicles, or, how everything's becoming more mobile, that creates more flexibility demand on there. And
Yeah.
storage is, in some form or the other, is going to be critical for us to be able to maintain that level of reliability that we need on the grid. And
Yeah.
so, like I said, DOE's plan is a Energy Storage Grand Challenge is a 10-year plan
Okay.
to set us up. And, we're seeing projections out where the U.S. will be kind of the leading consumer of storage in that 2040 to 2045 range,
Yeah.
just on the trajectories we're currently planned at. So,
All right.
yeah. And like you said, I think we're in a great position here to be able to leverage the resources that we have in the community to really create a central spot, a hub, of.
No, exactly. We did have a question from the audience that maybe before we go on to the next topic, you might help us with. And the question is how affordable are these systems for the general public, or is this for power grids? And I think, they're probably referring to like a Tesla Powerwall or something. If somebody on their own home maybe invested in solar and battery storage, and I know that you guys are more focused on the grid and overall, but do you have a general rule of thumb that you look at? And I guess it probably depends on your location and how much solar you may have aspect to, and then your local utility rates. No, a lot of variables, but do you have a general answer to that, Vince?
So we have seen inroads to, like you mentioned, the Tesla Powerwall in California, with the what is it, self-generation incentive program, there help buy down the cost of those Powerwalls, for residential systems.
Yeah.
I would say overall they're still probably more expensive than most people will afford. To be honest, you can go buy a generator, to have that kind of resiliency for your home, much cheaper.
Yeah.
But we're seeing dramatic price reductions in especially lithium ion technologies. That's being reflected probably more at the grid scale level in terms of getting more people interested. For the vast bulk of the country, though, and to get kind of wider scale penetration, we've got to have significant cost reductions. We've got to start, systems at a grid scale, and you can look at it different ways. They give you what just the batteries cost. Well, that battery by itself is not good. You've got to have some way to connect that to the grid and take DC to AC and your power conversion system. You've got to have a management, system. And you start talking grid, you've got containerized and then hooked into the grid. And so we're looking for lithium ion systems probably on the order of $400 to $450 per kilowatt hour is what they're costing at the grid level now.
Okay.
For a lot of applications, we need to be somewhere around, 4 times lower, around $100 per kilowatt hour to get widespread, and that's throughout the entire thing, throughout the installed. So that's power electronics, that's communications controls, integration cost, and all that needs to come down. You're probably still seeing that level for residential systems, and it will be a little more difficult to get that down. But
well, but I think that's a great point, right? Like in California, they're trying to incentivize people to do things on their own house if they can do it. But when you talk about the grid, now you're talking about, these potential efficiencies or taking carbon out of the generating system that kind of benefit everybody and applying it to all the customers. And I know, from our utility partners across the board, there's a lot of people that, get different types of subsidy programs to just be able to pay their electrical bill that they have today. And so, the whole mass of electrical users, I think that's the overall goal, right? That when you're talking about grid storage, that you got to bring the overall cost down, give renewables that ability to do, matching the load and all those things. And that's a great point. We've got a question about fuel cells, and maybe we can talk a little bit more because those are a lot of the research areas that you're doing at PNNL. Talk about some of the different storage systems. I mean, we talked about hydrogen or pumped hydro. These kinetic systems. I've seen the pictures of these tower cranes with concrete blocks.
Yep, the gravity.
Yeah, like a big old cuckoo clock or something, right? Or I mean, What are some of those areas that maybe PNL is looking at, or working on, about this? Because obviously, and then even on Grid Storage Launchpad, will you have other ways to integrate that up to 100 kilowatt test system into the grid storage, or will it really be focused on electrical storage batteries?
So
I know
back
that's a big
to,
question. That's like a
yeah,
five.
yeah. We'll divide this up into.
Okay,
So,
thanks.
so when we look at storage, I think you're right. We do tend to focus on batteries. It's the most tangible product to most of us is understanding battery chemistries. But yeah, hydrogen is a big factor. And let me back up a little bit. We focus on batteries, but if you look at battery usage, it is typically very short term. You're using it within that day, or soon. And we've all had that experience when I charge my cordless screwdriver up and I leave it charged and I come back for a week and it's completely discharged.
Right.
That is one of the problems with battery technologies is they have a self-discharge mechanism.
Right.
And so as you start looking at applications where I would want to seasonally shift energy from spring runoff that we have here in the Northwest to the summer demands, batteries are going to be tough to be able to do that. But a system like hydrogen, where you take that excess electricity that you may have, store it in hydrogen, well, now it's easier to store that gas than it is an electron in a battery, and feed it back. And so those are where we're seeing those applications where you may need what we would call ultra long durations storage, where you start getting into months.
Yeah.
Pump storage hydropower does a great job of that already, being able to do those aspects. There's people looking at thermal storage systems where you take concentrated solar from the sun and heat up a molten salt.
Yeah.
And then you just basically, how good is your insulation to be able to keep that salt molten until you use the heat to reverse it and generate electricity.
Yeah.
So, there's lots of different pathways to be able to get that. Some are going to work better at different time scales. Some are going to work better depending on what your local resources are in there. Hydrogen was originally looked at for teaming with nuclear plants. So you could keep it baseload operating and store that in there. What we're seeing today, like with hydrogen, we have an active program on hydrogen and fuel cells that are trying to do that. The fuel cell really is at the point where, you've got that hydrogen stored and you're trying to convert it back into electricity. A fuel cell is the most efficient pathway to be able to convert that back into electricity. But we're also looking at other aspects. If you break down the economics now, and you look at it in terms of the end product and the value of that, electricity is the lowest value end product that you can probably generate out of hydrogen. Going to ammonia with that, which has 4 hydrogens on it and nitrogen, and using that as fertilizer is a more economic pathway. Taking that hydrogen and turning it into some type of upgraded fuel is a more valuable commodity right now. And so, part of that is looking at the overall economics of that and what you want to get out of it.
And then on the Grid Storage Launchpad, will it be set up to use other storage technologies, or will it really be focused on more battery?
It will be focused, I think, primarily on the battery technologies. And so there are a suite of new technologies that are being developed that just don't have that infrastructure in place. So we've got lithium out there now. Lithium, we do not control in the US the lithium supply chain. So we are very dependent upon other countries and those relationships, for that. And so one option is we take the lithium and just replace it with sodium.
Yeah.
So sodium, we have all the access we want to, through the water. It's a little bigger, so it's a little slower, but that would be fine for most grid scale applications. And so we've got an active program there trying to develop, I would say, a sodium analog to lithium ion in there. That system still uses an organic electrolyte, and the electrolyte basically is there to basically allow you to transfer the charge from the cathode to the anode and back. That's the sole purpose of doing that. But that's what, when you have a fire in lithium ion, that's what's burning, that's what's catching fire. And so we've got systems that now are a direct analog, but then taking that next step for improved safety. And can I go to a water-based system to be able to conduct that back and forth?
Wow.
And so there, we're looking at, other earth abundant materials. Using zinc in there is very earth abundant. Aluminum, we've got plenty of supply. So things that we have access to that can be used electrochemically in a battery system, there is a ton of work just in that area. So Grid Storage Launchpad is going to focus on that.
Okay.
Now, there has been discussions about, what can we do in hydrogen, flywheel storage, which has been out there. I don't know if I see us going that far in there. We've got materials work that we're doing at the lab to look at and improve materials for flywheels. But, that's a lot of momentum in there as that's spinning.
Literally, yeah.
A different safety realm than we're used to with batteries. So, it'll be a decision like that. At first and foremost, we're going to do that testing if we've got the safety protocols in place that we can handle it.
I gotcha. And we did it on this question. I wanted to maybe go back to fuel cells and hydrogen and the relationship. Can you describe how a fuel cell works? And then, when we talk about hydrogen and like making hydrogen out of excess electricity, and then using that as a transportation source, can you give us a general overview of fuel cells and how hydrogen work with a fuel cell?
Yeah, so I'll actually back up just a little bit on there. When we start looking at how do we get hydrogen from electricity, is the first one, and it's basically water electrolysis. So you'll take a purified water stream through. You've got a membrane in there on one side of this electrolyzer that will basically segregate out one of the hydrogen ions in there. And so it purifies that from the water, and then it recombines to form the hydrogen gas on the other side. And so you do that by basically putting a voltage across there and driving that ion through the membrane. And then you get a purified hydrogen source. And so there is a cost. There's electrical costs associated with being able to do that. It is not 100% efficient, so you have a burden that you have to factor into it as you're looking at the economics. And so once you have that hydrogen, then you can, take it for other products. Hydrogen is typically, kind of a starting block as you're building up, a synthetic or fuel material. Or you can feed it back to a fuel cell. Now, a fuel cell is basically the reverse of the electrolyzer. We do not have, our driving force is now not electricity like we had in the electrolyzer, but our driving force is I've got pure hydrogen on one side and I have no hydrogen on the other side. And so there's a huge chemical imbalance in there. And that's really what makes a fuel cell work, is that chemical imbalance. It wants to reach equilibrium. It wants to have the same amount of, hydrogen on either side. It doesn't like having, nothing on the other.
Yeah.
And so there's a natural driving force for that to disassociate, drive across the membrane, and then recombine in this case with oxygen to form water on the fuel cell.
Yeah.
And so but that chemical driving force gives you the high efficiency that you have at fuel cells. So we in the lab, it's a different type of fuel cell that we do. There's two types. There's what's called a polymer electrolyte membrane fuel cell. And so, as the name implies, that uses a polymeric membrane to do the hydrogen separation in there. And those operate at low temperatures, very low. And those are typically used with pure hydrogen systems. At the lab, we have another type that we're developing that's called a solid oxide fuel cell. And so this one actually operates at very high temperature. It changes it a little bit in that it's doing the oxygen ion out of the water instead of the hydrogen in there. But what it enables you to do is to use much more than just hydrogen with it. So fossil fuels or anything else, anything that can be oxidized, is a fuel for the fuel cell to keep that driving force going in there. And so it does give you additional flexibility as you need in the systems. But we've demonstrated several of these systems to be upwards of 75% round trip efficiency. That's the pumps and everything, you know, whereas
Yeah.
we're typically talking, you know, 30% for some of the best, you know, internal combustion engines, you know,
Right.
typically 20s
Yeah.
in there. So it can be extremely efficient in terms of conversion of a fuel into an electron.
Okay. And I think did believe that you got a patent for solid oxide fuel cell technology.
Yeah, that was what that's what I went to grad school with. That's what
Okay.
got me to the Tri-Cities was
Okay.
fuel cells. And then, yeah, then we've worked on other things. Well, I hope I still got you. I may have lost you here. Oh, there you go. So that may have been a hang up on my end.
Yeah, I'm sorry. No, I think it's on my end. I think school time just kicked in for our kids. You know, I think today's the last day before Christmas
break.
Yeah, I'm hoping I'll stick with you, but so what sounds amazing? What are some steps to that can hear me?
While Karl's getting back on, I'll kind of take over for him.
Oh, okay.
Sorry about that.
No.
I think I'm back now. Thanks, Tracy. So I apologize for that. It's the technology age that we live in.
Oh yeah, my son will start gaming here pretty soon, and
right.
I'll have my issues. So
right. So the solid oxide fuel cell, what needs to happen to get those to commercialization? I mean that out of like a hydro fuel, that's amazing, right? Because we all know, or generally know, diesel engines are more efficient than gasoline engines. They essentially make more power out of the same power density and stuff. So I mean, 75%, that's incredible. Is there, what can we do with that, or what's the lab doing with that technology?
So we're still trying to push it. The biggest issue right now with that technology is the cost.
Okay.
So these are typically, ceramic materials that have a costly fabrication process. To get those in the right format, they have to survive at, greatly elevated temperatures that corrode most metals.
Okay.
In there. And so that's been the biggest problem with it, is just the cost element.
Gotcha.
The other thing that happened in there, in the development of it, was low-cost natural gas. And so efficiency gains that you would typically have, the economic benefit went down when the cost of natural gas went down.
Yeah.
And so as you were doing that trade-off about whether to invest in a new technology that's X amount more efficient, in there, if your feedstock material drops dramatically, it changes the economics of it. But it's still there. I think we see a lot of applications, though, for fuel cells that are always going to have a cost element. But, as we look at a future, batteries, especially like for electric vehicles or any other things, are inherently limited. Their energy is fixed.
Yeah.
In there. They're not a generation asset. They are a fixed energy asset.
Okay.
And so teaming, like in an electric vehicle, a smaller battery pack with a fuel cell that runs off hydrogen that can recharge the battery pack.
Mm.
And so you use the fuel cell as a highly efficient range extender for electric vehicles.
Okay.
And so it's there to augment. And I think those are the type of hybrid type systems, that we'll probably see in the few years as we see more electric vehicles. And, we're going to be up against the limit of just how much we can store cost effectively and weight, on an electric vehicle. And so having a small fuel supply on there that extends the range, reduces range anxiety, and also, it can overall improve performance. I think we'll start to see those systems come out, but they'll be much smaller than a traditional power plant. That's all fully composed of hydrogen.
Yeah, and the question that we had earlier about fuel cells talked about the supply chain, and we talked about the, U.S. doesn't have lithium, and then you talked about some of the research labs doing to look at different elements that could be used in battery technology. But with fuel cells, or like traditional hydrogen fuel cells, what are some of the components that go into that? And are there supply chain issues, or is the U.S., like in our natural resources space, well positioned to, to be more of a leader in the hydrogen, traditional hydrogen fuel cells?
Yeah, so I would say one of the, we are positioned, and a lot of credit goes to DOE for positioning, U.S. industry. They've worked heavily with them so that membrane suppliers are here. There's multiple ones in the U.S. Everything. The biggest issue, like with the low temperature polymer ones, is the best material to use to either break apart that water or recombine it is platinum. And you don't need,
which is the highest cost, right?
It is. It's better than it was, but
right.
But yeah, it is an expensive element, and so there's been a ton of R&D work to see, can I replace this with lower cost catalyst in there than platinum? And I haven't kept up in the work in the last few years, but
sure.
Everything I saw was, we can get 30% of the effectiveness of platinum, and it's just, we do not have a drop-in replacement for that platinum in there. And so but there are other efforts that they're doing that are, driving the cost down of that. But that's always kind of been the big sticking point, is active platinum management of those systems.
And I think that, you did, I think you've done a really good job today, Vince, in kind of explaining the role of DOE and the funding for research that you guys are doing at PNNL and the other national labs, and that interrelationship with corporate America, if you will, or industry, and that when the federal government invests in the research that you guys are doing, it's offsetting some of those costs that private industry necessarily can't afford to do on their own, right? To perfect this next new technologies, but being able to have that forward visions is what both positions the U.S., for being a leader in these technologies. And it's great to hear you explain it, because I think it's something that we forget about, right? Like we read the article about the new battery or the new fuel cell or the, renewable or something, but there's really all this work that's been done for so many more years before that, like the work that you guys are doing, that really, as a consumer level, gives us the chance to access that technology in the future, right? Like it's a cool story. I appreciate your description of it.
Oh, well, thank you. Yeah, it's been interesting, getting into the DOE system, where you really start to figure out our job is to de-risk new technologies and do that to a point where we understand what the handoff is going to be with industry. And so what do we need to get a technology up so that industry will take it and want to buy off and do the final commercialization of it? That's not our job, but find out the big problem areas with it. Does it have potential? And if it has potential, what are the stumbling blocks? Can we take the risk out of those stumbling blocks and make it and get it to a next level state of maturity?
Yeah, that's really cool. How about on my list, and we're kind of coming up on, looks like 9 minutes now, but how about flow batteries? I know that's something that that I've read a little bit about, and I know in a lot of PNNL things that I've listened to or heard about, there's a discussion about flow battery. What is a flow battery, and how does it work, and how is it different from what we think of as a like a lithium oxide battery or other technologies?
Yeah, and it's a great timing to bring that up, because we've talked about the other ones. So I can point out the differences now. But so flow batteries are a little unique in that. So I'll take a step back. If you look at traditional lithium ion, when we talked about graphite or silicon or a metal oxide on the cathode, what we actually do is we pass an ion through that electrolyte, and it's basically absorbed into the other material. And so it'll be what we call intercalation. And so it will go in, that material will expand when it accepts the lithium, and then it will contract when the lithium comes back out for the other part of the process. So your energy and how much lithium you can fix is based upon the material's ability to accept that lithium.
Okay.
What we do in a flow battery is we throw that all out. And so we start with basically just facilitating first that electrochemical reaction, and so we will have something where it's not actually storing, but you're passing the electron back and forth across that, but it's reacting in a fluid that is being pumped on the outside of it.
Okay.
And so you have two tanks on the outside of the system that's pumping what would be your positive charge and your negative charge through here.
Okay.
And then so you're transferring that electron into a fluid versus into a material that's got to expand. And so what this does give you, it gives you two things. The first one is my power and energy are now completely separate. Before, the power and energy are dictated by how much I can get in that material and how much I can access. It's all contained within that. Here, I can make my tanks 4 times the size if I want to have longer durations energy storage.
Okay.
The other thing does is we look at this, especially for utility applications. They are used to a 20, 30, 50-year asset in there. Every time I stress a material like in lithium ion, that I'm, expanding it and contracting it, you're stressing it. That stress limits the lifetime. And so now we've got a battery system we can do it where we do not have that same type of stress. That's in there. This is a fluid that we're just transferring an electron back and forth into. And so, there's potential. We've seen systems in Japan of flow batteries that have gone through about 17 years, I think was the last I heard, of continuous operation. And so that's really a kind of a game changer in there to be able to have that longevity and then also being able to separately scale up the power, or energy if I want it. So no, it's great. And so if you look at it, when we started this program, and this has been one that PNNL has been known for, is our flow battery research. It's been a really strong suit. But we had to go out and hire people that had fuel cell experience. Because no one had that. And so they're used to flowing hydrogen on one side, doing that electron transfer, and then taking water out. So they were the closest we could get to people that could understand how that flow battery would work and do it. So all of our initial people that worked on flow batteries were all out of hydrogen fuel cell technologies. But no, we still view it as a viable alternative. It is, the great things about it is we're using water-based solutions. And so I've got the flammability risk, the safety efforts, all that's lower. What we got to do is you do not have the manufacturing infrastructure that you have with lithium ion. And so keeping that, it has a lower cost trajectory, but kind of getting those supply chains and everything else in place to be able to support that lower cost is probably our challenge right now to get those more active. First generation systems used vanadium, which is costly and we do not control. So the next one's what we've done at the lab or working on is, can I take that vanadium, which is a beautiful element that can change charge very easily, but can we take that and replace it with an organic molecule that we synthesize at scale, we control, and those types of things? There's some challenges with that we're working on in terms of long-term stability and that, but we really see that as the next generation that we can get, I would say, cost competitive with the other technologies that are out there. With enhanced flexibility.
Yeah, and a flow battery would have more of an application. I mean, I'm not going to get a flow battery for my screwdriver, right? But on a big scale system, what you're describing, that would be more the application for a flow battery.
Yeah, flow batteries are always going to be larger than lithium ion systems. And so there was one company a few years ago that was trying to do one for electric vehicles, and they were not successful. So they are built for pouring a concrete pad and putting it at a substation. Yeah.
Well, and even and this is what I read, as I was kind of getting ready for talking to you, but a lot of the research that you guys do, happens at the molecular level, right? Like you were just talking about synthesizing this organic molecule to replace vanadium. Well, that's an example there that you and your team are really focused on being able to do, and really breaking it down to that molecular level, where kind of the industry role is over here, that once you've, got that technology to a point where you can commercialize it, then they take it and put it into production stuff. But unless you do this molecular level research, you're not going to create an economically viable product that somebody can go build and sell, like in a flow battery, for instance, right? And that's again, that interrelationship and that role that you and your team and PNNL and DOE play with industry, and how we're going to change the future. And that's a great explanation that helps a layperson like me to kind of understand, like, why are you and your team at PNNL so critical to, both our local economy, but then also in setting the standard for future electrical storage and so many things that you guys are working on.
Yeah, and it's been great. Those fundamental science tools that we have to be able to apply those to actually solve real world problems. What we typically is, what's great is when we have industry coming in with, here's the issue, here's what we want to see, and being able to take those tools and understand, okay, here's why it's degrading, here's why it's doing this, and then can we develop, from those tools a fix, and then hand that back to industry, once we have it. But it's doing that fundamental science, I would say, in a targeted manner, so that we fully understand what the end problem is a great aspect. And I think something that, if I can brag a little bit on, we've done a very good job of here in terms of, trying to get that voice of industry, but then bring the tools we need to solve the problem.
Yeah, no, that's great. Is there, just out of curiosity, and this will be our last question, but is there, just like you started out in industry and then you kind of made the transition to, to the national lab DOE side, like with people and researchers and professors like yourself, is there that, people moving back and forth, or do people generally have a career path that's either one or the other?
Yeah, I would say I've seen different pathways that come in. I think a lot of people either come out, as they're going through graduate school, and go, I'm going academia, my job is to be a professor. And so there may be a stint at a national lab, in that pathway to get some experience, or even some in industry. But then I do see a lot of people that go, I'm much more industry focused, but they fall back to the lab because it's a nice mix. I still get a good problem mix and solving a problem. But at the end of the day, we're focused on solving the problem and not necessarily a bottom line, in doing that. And so a lot of people I've seen have migrated from industry back to the labs just for the freedom, that it gives you to work on the technical problem. Oh,
that's great. Vince, this has been great. I think we could probably have you on for 4 or 5 different times the whole time. It's really interesting to me, and I appreciate your discussion today, because it helps a layperson like myself to understand some of the things that we read the articles about. And, like you said, people solve grid storage and, all these electrical problems every day in articles, but, what you guys are really doing is, making it work, putting the rubber on the road. So I really appreciate your time today. Do you have like a closing remark, and then we'll wish everybody Merry Christmas?
All right. No, I appreciate you having me, and I would love to be back at any time if you want to have more discussions. But no, this has been great, and it's been fun. I always enjoy talking about energy storage and batteries and technology. So it's been fun. Thank you.
No, yeah. Again, we really appreciate your time and for PNNL to make you available so we could have this discussion. We will have you back on in the future for sure. But wanted to wish everybody a happy holidays, Merry Christmas, and enjoy the new year. We're going to take a break, and we'll be back with Coffee with Karl after the new year with some great guests like Vince. So thanks, Vince, for your time today. Everybody have happy holidays, and we'll see you next year.
Thank you very much.
Thank you.